Welcome, welcome to the pre-recording of the second half of Lecture 10. In the first half, we introduced dynamic programming with the problem of weighted interval scheduling or planning, an original name for programming. In the first part, we also introduced the technique of memoization. And as a technical the technical aspect of this second half is that the memoization will lead to a direct iterative algorithm. So I hope that this is our first example, the weighted interval scheduling, which we will elaborate in great detail. There are exercises that allow you to explore alternative problems, and that should make you familiar with the technique of dynamic programming. So it is another algorithm design technique. Earlier in this course, we spent an entire chapter, or at least the textbook spent an entire chapter on greedy algorithms. You localize, you make something optimal locally, and then you show that it also works globally. This is often a direct way to work. We then considered, and that was the next chapter in the textbook, we considered divide and conquer. Merge sort is a divide and conquer technique. Fast Fourier transform, Strassen's method. So there are many important algorithms there. Also with greedy algorithms, I should say that we had a lot of scheduling techniques there, and also algorithms that involve graphs. So finding the minimum spanning tree is one of these problems that is solved very efficiently by greedy algorithms. Now, greedy algorithms, we solve optimization problems. And I should say that in computer science, we always optimize something, if not the running time. Now, of course, it happens in our applications that when we apply greedy algorithms, it works, of course. But in practice, there might not be a greedy algorithm available. So then what can you do? As we did in the first half of this lecture with the weighted interval scheduling, we started to explore subproblems. In some sense, divide and conquer works similar. You divide it in subproblems, you solve the subproblems, and then you combine. Here, actually, it looks as if we were doing an exhaustive search. In that sense, it's quite natural if you care mostly about the correctness and your problem sizes are small, then brute force methods work. In that sense, dynamic program is a natural technique. But on the other hand, it's kind of worrisome. So even if there exists an efficient solution, a recursive formulation can get you into problems. Okay, um, memoization. So we solve optimization problems recursively because that's a natural way of thinking. Also then very naturally to prove the correctness. So if you work with recursion, you break things up into smaller problems. If you can solve the smaller problems correctly, then, and if you do the combination good, and often this is the taking of the maximum of two numbers, as in the weighted interval problem, then you have the proof by induction of the correctness of your algorithm. Now, it looks as if we are doing an exhaustive search, but we are also pruning in the tree of all possible choices. So that's one thing. And we observe, and that's the second thing, that there is a huge overlap in the problems that we solve. When we look at the tree of recursive function calls, we recognize subtrees that are in there. So, and with divide and conquer, we turned efficient algorithms that ran in quadratic times into subquadratic times, like with the fast Fourier transform or with merge sort, or with matrix multiplication, cubic time becomes subcubic time. Here, actually, memoization is a technique that pays even off more. So, an exponential time recursive algorithm turns into a polynomial time algorithm. So if there are techniques, some techniques are uh, more worthwhile to remember than others. Memoization is a very time-saving technique. As a technique, we will come back to this in this second half. As a technique, we will see that it can be used to derive a direct iterative version. And therefore, you have almost also the optimal implementation of your algorithm that solves the problem. Okay, so here is the memoized version of the computation of the Fibonacci numbers. So if you forgot what the Fibonacci numbers are, here is the definition. So we have the first two Fibonacci numbers, 0 and 1, and then we compute the remainder ones via the recursion. So the recursion is encoded in the else case here. You see the two base cases, and then you have the general recursion. Now, with memoization, we avoid the exponential growth of function calls by storing all previously computed values in a table. So in the memoized version, we are always first going to consult whether we have already computed the end Fibonacci number. This is just to check if something is there or not. So you can initialize your table here in this case with -1, and accessing an array is constant time. So what this means is that you will compute every value only once. So when this is running, you can check that the table of values, you compute n values, but you assign only once. So it's important to see here that this if else, so only one of these branches is executed. Either you consult it or it is for one of the entries that you haven't computed yet. So that was key in the proof of the cost of our weighted interval scheduling. It's also the key here to show that this algorithm runs in time linear in n. Linear in the input size and actually also linear in the output size. So you compute actually more, not just the end Fibonacci numbers, but you also compute all the previous ones and you store them in this table M. Okay, so let's derive from that an iterative version. If we are running the memoized version, we start with 5 here, and I am going to store the memory table in a list. So for those of you who are familiar with Python, this could be the running of a Python script where you, in the first call, the list here is allocated and assigned to the address to which M refers to in main memory. So you see that in the recursive calls, you are going to assign only starting at the base case. And then when one returns from those calls, one is going to assign to the subsequent values when returning from the calls. So this is also a tree of recursive calls, but here making the point again, you can see you can count the number of assignments, and we only do 6 assignments here. So when we are computing the fifth Fibonacci number. Okay, so this is by observing. We are implementing this algorithm and observing really that the number of calls, the number of assignments is actually um, linear with n. And the point of making an iterative version is that instead of computing this table backwards, so you start to make calls whenever you need it, you can compute this also progressively. So if we are now focusing on this table M, then we see the evolution of this M. And this evolution very naturally follows the progression of the table. There might be something quite odd. We first compute the n minus 1 Fibonacci number before the n minus second Fibonacci number. So the two assignments here, comma 1, means that we are assigning to 0 at the zeroed position then later, which seems a little bit natural, but I kept unnatural, but I kept the original version of the algorithm. So if you see the progress of this memoized, this memory array, then you can derive the initialization, and you see that in the for loop we actually add one element. So the notation from Python suggests a list, but actually you can perfectly well work with an array of n plus 1 elements. And this is the natural direct algorithm to compute the Fibonacci numbers. Now, of course, if you look at the problem, you say, yes, of course. How could you do it in any other way? But the point of dynamic programming, memoization, and the direct iterative version is that, for example, for the weighted interval scheduling, we did not arrive at this way of thinking. So the correctness proof follows still via the recursion. If you want to show that this is correct, then you still have to go back to the original recursive definition of the Fibonacci numbers. Okay, so let's look again at the weighted interval scheduling problem. So that was a problem where we had a set of requests, start, finish time, and value, and we wanted to compute a set of non-overlapping intervals so that the sum of the values was maximum. So we do this recursively, or if you prove the mathematical correctness on induction on the jth job index, j here. In the memoized version, which was derived in the first half of this lecture, we look up the value, the optimal value of the selection of the first of the jth request or the first j minus 1 request, whatever. So in the base case in the recursion, we had 0 when there was no requests at all. That was a very straightforward base case. Or otherwise, we had this function P. So P was the first request with highest index that could still be scheduled when we scheduled the jade request. So if we schedule the jade request, we have its value that's added to scheduling the old request, the first one, up to that request that doesn't overlap with the jade request and that we can therefore still schedule. So that's where the P also is the previous last request that we consider, but it's also the P from pruning the search space of all subproblems. That is also what makes it so very efficient. And the other way, of course, is that all the subproblems are overlapping. So that is also where it starts to get very interesting. So if you don't select the J the Jade request, then you have to consider all the previous J minus ones. So you have this choice. We store all those optimal values in the array M before we return. So the point of this memoization is that we avoid the exponential growth of the function calls. In the efficiency, it was also very important that every step in this algorithm ran in constant time. Accessing an array, assigning a value to an array, doing a plus here, and taking the maximum, that are all constant operations. When we return from the recursion, but also here in all these steps, so you prove the efficiency. So this algorithm runs in linear time. It's very efficient. This algorithm runs in linear time. You prove this by induction. So I'm just saying that the recursion here also has a lot of information in there. So in some sense, it's an efficient version, but it's perhaps not still the version that you want to implement. Um, some older languages, older versions of languages actually do not have recursion. So you could also see it like this. Dynamic programming was invented in a time when, or was developed in a time when languages were not yet as flexible. And doing recursion, running it requires actually also a heavier runtime environment. Okay, so what is now the whole point? The whole point is that just like the Fibonacci numbers, and actually it's simpler than the Fibonacci numbers, we only have one base case. And it's a little bit more complicated because we have this function p there. And p, as I said in the first page, you can treat as an oracle. So it's also running in constant time. If you consider the actual implementation and if you think about the fact that we are having to scan potentially all the previous jobs, then it might not be so straightforward, the linear time running costs. But here you see it. So, and what can be more simpler than this? So why didn't we start with this? Well, it's not obvious that this is correct. So the proof of correctness follows from the original recursive formulation, which was using the original observations and also led to the introduction of this function p. But here it's obvious that this is now a progressive way of computing the memoized table M. So let's see how this runs. So this is the iterative version. And I realize now that I should have had somewhere the picture in there with all the intervals. So we have the requests, 6 requests. Um, we have the index j from 0 because we have to deal with the base case. And then we have all the values for p. So here you see that indeed p, it's treated as a function, um, but it is actually an array. So it is given to us as a table. So it is pre-computed. Okay, so this is how we start. And now we progressively run to this, each time taking the maximum value. So it seems like we are running to this. So we each time take the maximum of the two. The maximum of the current job. So perhaps I went too fast and going from 4 to 6. So we are considering actually the sum of the previous element in the table, which is 2, and 4, which is the previous value. So we have here the 6 comes from 2 plus 4. And then we are considering the previous value, which is 4. So we are computing, we are at j equals 3 now. We are computing 6. And 6 is arising as the maximum of 4. I'm sorry. So it's arising as the maximum of 4. And this 2 here. And how do you get to 2? Well, you have to use this index p of 3. So the logic of this progressive way of computing the values m is actually running entirely equivalent to the recursive solution, but it's not entirely obvious that what we are doing here is the same as what we've done before when we derived the weighted interval scheduling. So I hope it is clear how this table is constructed. So we are computing the values in this table. So for each table, we compute the optimum value of the selection, what we obtain. Okay, obviously, it's a linear time algorithm. Uh, Prove that this iterative compute opt is correct. Um, so this would go also by induction. So if the previous n minus 1 values or the previous j minus 1 values are correct, then the jth value will be correct. In the first half, we showed that we can retrieve the selection from this. So that is another potential exercise. Does the iterative method also give you the optimal selection of the requests? So what we computed in this m value is essentially the sum of the values that is optimal. It doesn't really say directly what is now the selection. So this is actually an extra exercise. Okay, I'm actually almost towards the end of the second half, or the end of the lecture 10 entirely. So we considered as exercise 2 the number of ways how you can parenthesize a multiplication. So multiplication of compatible sized matrices. So whether you whether you put the parenthesis in one way or another, you get the same matrix on return, but the number of total amount of operations, so the total number of scalar operations may actually differ. So that's why you may want to think about if you have to, and you can already compute the number of operations you have to do, the number of operations and multiplications you have to do, you can already compute this and see why it actually matters. Okay, in the first part, exercise 2, you applied memoization to compute this sum. So the sum gives you the number of ways you can parenthesize it. This can be computed very efficiently. And likewise, you can actually compute for every possible way, then very efficiently, the minimum or the best way to do this. Um, so that was the exercise 2. Now, this exercise, you suggest you do this after exercise 2. Derive a direct iterative version of the algorithm. So you're going to compute all the values for S in a memoized table. The recursive version starts with a value of n that you haven't computed, and then actually start to look up in the array S and do the multiplication. So this can be running, the iterative version can run, the memoized version, sorry, runs in linear time because you only compute one multiplication for every value n. So that's what you actually can have to show in the that you have to realize now if we get to this exercise, and also you have to prove the correctness again by induction. Okay, now to end, we have now two efficient algorithms. The memoized version has the benefit that it still shows the original logic of the recursive formulation. So that's kind of the middle version that you have to com con actually that you the version that you have to remember. So it's memoization, it's on remembering. So this is kind of the middle way between the very inefficient original recursive formulation, correct but exponential time running, and then the direct iterative algorithm. That's actually the algorithm if it comes to coding, the more very restrictive way of programming, which we also don't really use in this course. But if it comes to coding, then of course the direct iterative algorithm is the one that will give you the fastest running time. Running time now in actual times. Okay, so we are seeing many ways to solve the same problem. They are connected, and the code itself is very small, but the reasonings are most important. So what goes in between the transitions from one algorithm to the next, uh, that is often critical. Okay, summary. We see dynamic programming after greedy algorithms, after divide and conquer, because it takes a little bit more creativity to apply dynamic programming. But here are some guidelines. So if you split things up in subproblems, it's important that the total number of different subproblems doesn't grow exponentially. If you still have to explore many subproblems that do not overlap, then dynamic programming will not work. Often for it to work so smaller problems can compute it faster. Uh, there should also be a natural order from the smallest to the largest subproblem. So, as with divide and conquer, we have seen that often it can go wrong. Often we do a lot of work without gaining anything. Sometimes you have to spend more work in how you subdivide and sometimes how you combine the subproblems. Okay, so this concludes lecture 10 in this 4-week summer course. It's in the middle of the fourth week. In the next lecture, we will start to review for our midterm exam. This is also the middle lecture of all the lectures that we will see during this 8-week summer course. So this is an important milestone in the course.